I think you'll see some math tricks that you can add to your toolbox. But you also have to balance the math with the interpretation of what's going on. And so there's a lot. That makes it a little bit richer, a little bit meatier of a lecture. It should be good if I don't mess it up. But you know how it is. And okay. So we do noise at the end of the semester. Noise in AM systems is what we did last Wednesday, and today we'll do noise in FM systems. There's a reasonable chance I'll get all or most of the way through this material today. If not, we'll pick it up a little bit on our last class, which will be Wednesday. I'd like the last class to be pristine so I can talk about shot noise, which is an easy-to-grasp fundamental noise source that will give you a little bit more maturity on noise. So today we're going to review angle-modulated systems. That's phase modulated and frequency modulated. And we're going to do it with a little bit of a twist by injecting noise. Remember, right at the very end of the channel, when the signal's at its weakest, we introduce a noise term so that we can and then see what that impairment means to our signal-to-noise ratio. With FM and PM, as you can imagine, the math is just a little bit more interesting. Just a little bit more interesting. So then that's what I was talking about a little bit on the preamble here. The math is interesting and should not quite challenge you, but remind you of some of the things you can do with complex signals. And then the thing that'll be really interesting for you, I think, and I know that you guys will respond to this and will enjoy this, is keep in mind the physical interpretation of the math. You know, you'll be able to follow along the math, and then with some good attention. But don't stop there. Do what I always try to, guide you to do, which is look at the physical interpretation of what we're doing, and that'll be an interesting on this lecture. That'll be interesting for you, and it'll kind of keep you alert, hopefully. Okay, and ask questions as you always do, and we'll get through it. So we're going to look at noise in angle modulated systems. And remember, the nice thing about angle modulated systems is if you do FM, you know PM right away, and if you do PM, you know FM right away. So if you do one, it's a simple filtering operation at the beginning and at the end to turn it into its other extreme. Again, that's something that we'll see and be reminded of in more detail as we go down the path. And so what we'll start with is an FM, or in fact what we'll really start with is a PM modulator. Input a message signal into that. And this is our transmitter. We will go through a channel. And what we assume here is that the channel attenuates the heck out of the signal. That it really, we want to get every last meter out of our transmission. These are expensive systems, and we want to hit all the market, or we want to hit all the distance from city to city. And so at the end of the channel, our signal is really hurting. And it's at that point that we mathematically, in our modeling, we put in our noise. So sort of a worst-case noise accumulates right at the very end of the channel. Now, in actuality, as the signal goes through the channel, noise is continually adding to it. But that's an integral, and it's much easier and much more of a worst-case scenario to put it at the end, to add up all that noise and put it in as a signal at the end. The other thing I wanted to remind you of, and again this will come out in more detail in a few minutes, is the nature of M of t and the nature of N of t are kind of two sides of the same coin. The message signal should be sufficiently random that it has information on it. It has a rich array of information on it. And the noise is random because it's noise. And so how do you separate the information, the random information, from the random noise? And the answer is you can only sort of do that. You can't fully do that. You're just sort of stuck with that intertwining of signal to noise. Our first separation, and our biggest separation, is this bandpass filter that we have that we have at the gate, at the input to our receiver. And this is like a window. The wider you open up the window, the more you let in, signal-wise and noise-wise. And what you want to do, we look at this bandpass filter in the frequency domain, and we start narrow. And when this window is closed a lot, we miss out on a lot of our M of T, but we only let a sliver of noise in. So we're sacrificing our message signal, but for noise. As I open this up, I let more and more and more message signal in, and I let more and more and more noise in. The thought process is, as long as I have message signal bandwidth, as long as I have a message signal there, I win by getting more and more message signal in, even though I'm adding more noise. At the end of when I reach the end of the message signal bandwidth, and remember that's an ambiguous concept with FM and PM, not like the AM's case. That's really the best place to stop, because if I open up my window further than that, I let in no more message signal power, but I continue to let in more noise power. Okay, and so from a systems perspective, that's why this bandpass filter is really, really important. And in an immature technology, what you're generally stuck with is a bandpass filter that you specify, hardwire in there, and leave it be. Okay, and sometimes in the optics world, not too long ago, you were there with a little screwdriver adjusting the skirts of this bandpass filter, just so, and then you would leave it for 20 years. Well, how primitive is that, right? Nowadays, or especially in those very, very expensive backbone systems, you actually make a measurement of the quality of your signal to noise ratio, and you adjust the 2 3dB bandwidths and the center frequency. So you can actually slide this bandpass filter over, certainly over the lifetime of the instrument, of the system, and even more quickly than that if you're willing to pay a little bit more for an adjustable filter. And you can imagine the gains that you would get given that feedback loop to that device. Okay? That should be ringing bells in terms of how do you look for inventiveness in systems to come. Yes, sir?
I was just wondering, if doing that filter digitally would make it a lot easier.
So the question is, can you do this digitally? And certainly, if you're doing wireless, the signal processors today are blazingly fast relative to wireless signals, and so you can absolutely do that. And in fact, that's the nature of these digital software, user-defined software-defined radio systems. And so, yes, the DSP revolution has opened up a whole bunch of not just the primitive moving of this filter around or adjusting the width of it, but actually really tailoring notches perhaps in there or the tails to just eke out all the energy in your signal that you possibly can on a real-time continuously adjusted, reconfigured nature. Now, when you get up into the optics world, 10 gigabits per second is a slow optical system that's the preponderance of the market today, but people have 100 gigabit per second links. 400 are in development, and a terabit per second system is also in development. And digital just doesn't cut it yet out there. Maybe it never will, but I never say never when it comes to technology. Yeah.
Is that the limiting constraint of the current speeds that are available then? Is that
So is the signal processing the current constraint of the line rates? I think, I've never had to answer that question before, but the way I'll answer it is when the silicon germanium signal processing kicked in, then all of a sudden the coherent detection of those systems became much more achievable. In other words, having a laser, okay, so you need on the receiving end, you need a local oscillator. Well, in the optical world, what is that? That's a laser. That's a laser at 197 terahertz. And so what you do is you take your photodetector and you have your signal coming into your photodetector and you put on top of it the local oscillator, a laser beam. And that allows you to mix with the nonlinearity of the diode, the photodiode, and bring you back down to a signal that's easier to handle. That technique, that coherent detection technique, was well studied in the 80s, but didn't go anywhere commercially because, in fact, who one of the experts on that is? One of the world experts on that from that era is your lab professor Kiyosawa Cameron. He has marvelous works in the early, heterodyne or coherent detection of these systems. But it didn't go anywhere until the realization of the electronics and the signal processing came into play just a few years ago, and then it was just like a switch. So again, this whole business of, as an inventor, as a creative engineer, and especially, and this is the nice thing about this course is, you have this basic theory, and the theory is going to get tweaked and adjusted. The coding theory is going to improve over time, but really, you have to look at what components and how you realize everything. And it's one of the biggest tools we have is to take a look at certain elements and plot their improvement rate per year. Just plot their spec over the last, their operating spec over the last 5, 6, 10 years, and pretty much you can guess, at least forecast, where you should be over the next 3 or 4 years. And so that helps you plan your development cycles. It helps you plan your I'll even say your inventions. If so those are all very, very useful tools that we don't have a course in, but we bleed into courses like this, and I don't want you to miss out on that. So when you pick a specialty and in your tool, you look at your tools in your toolbox, you understand where they are today, but you also try to look at the slope and figure out where they're going to be by the time of the next design cycle, and then the next design cycle after that. And how long do you think a design cycle takes? Well, anywhere between 6 and 24 months, depending on the complexity of the project, and depending on the culture, the business culture of the company. Okay, how much they bite off per design cycle, Okay, and then those are things that you'll want to pay attention to, and maybe as interns you're already taking a quick look at that from the companies that you're working in. Okay, sorry, you guys get me off on digressions so easily, but that's okay. I don't think it's a bad thing. So after this bandpass filter, I'm going to look at the signal y of t. And do you remember? I started to talk to you a little bit about the role of this bandpass filter, and I want you to think in terms of what happens if I have what happens if I have a light bulb that has all the colors of the rainbow coming out. So these lights that we're sitting under here are a nice white glow, but we know. From high school optics or even earlier, that there's a rainbow buried in that white light. That is, if I put a prism in front of it, or if I bounce it off of a diffraction grating, or the back of a CD. Those old-fashioned things that were just after tapes and just before the MP3 players. Well, they're a beautiful rainbow, beautiful diffraction grating, and so you can see a rainbow off of those. Well, if you now take a slit and separate out, say, the green light or the red light, you get tighter and tighter and tighter frequency band, and that looks exactly like an amplitude modulated system. So you have a center frequency, You have a center frequency, depending on what color you separate out from using your prism and your little pinhole. But around it, you have some fluctuations because it's noise. It's filtered noise. And so that looks very much like an amplitude modulated system where the bandwidth of that amplitude modulated signal is the bandwidth of your filter. And we used that last time. We used that technique last time. And remember at the end of class I said, over the weekend, think long and hard about this. Okay, because it allows us to write down a form for the noise after this bandpass filter. And in fact, what I'll go ahead and do is I'll remind you of what that form is. The noise is a function of t, and I'm putting it right after the bandpass filter. Okay, my notation is crummy as usual, but this is the filtered noise. It's gonna have a frequency component. It's going to have a frequency component at the center of this bandpass filter. The center of this bandpass filter is going to be at the carrier frequency. I won't kid you about that. I might on the test. I might change that up on the test. But it's going to have a carrier frequency. The same. We're going to match that to the carrier frequency of your transmitter. So it's going to have that. It's going to be centered around there, and then it's going to have some amplitude fluctuation. And I'm going to write that as n sub c of t in front of the cosine. So that c is for cosine, and that c is for carrier. I'll say that again. Just this c here is for the cosine, and this c here is for the carrier of the system. So you see that because this is S for the sine. And do you remember what we called this term and this term? Yes, this is the in-phase term. And you're absolutely right. This is the term that is out of phase. It's 90 degrees. And by the way, the modulation here takes care of the overlap. And one of the things that will come out of this lecture is exactly the trig for that. So you're absolutely right. This is the out of phase. But that wording is only worth a nickel. And there's a $5 word that describes it. And the quadrature. Yeah. So you're absolutely right if you're trying to understand this, to think about this as the noise that is out of phase to the carrier frequency local oscillator. But if you're talking in conversation and you really want to impress the people around you, then you have to use the word quadrature. Okay, this is the way it is. So this is this, and this gives rise to the noise power, and as a function of frequency. And just to remind you that for the angle modulated system, the bandwidth was 2, and I'll write it slightly differently here. It's the sum of the frequency spread, the range of the frequency that's moved by m of t, and then the natural bandwidth of the signal b. Remember, we divided that and we called that beta. But this is just I'll write it just a little bit differently to force you to go back and refresh your memory on that. The exam is coming up, and you're going to do that anyway. Nothing wrong with what I wrote. So then just to complete my system block diagram, I have the FM or the PM demodulator, and then I'll do some filtering at baseband. And what I will get out is the signal power out and the noise power out. Okay? So eventually this term here is going to lead to the noise power out. Notice the end there. I think this is Lottie's notation, and I'm trying to be a little bit cleaner. And so I have the signal power out and I have the noise power out. Oh, and then the last thing, this is the noise treatment, but we want to review the form of the exponentially modulated signal, or the angle modulated signal, and that's equal. Let's see. That's as a function of time, and that's going to equal some hopefully constant amplitude. Hopefully constant amplitude. We'll talk about that in just a heartbeat. Times the cosine, and our message signal is wrapped up in the phase, the time varying phase of the time varying phase, so that for phase modulation, that phase angle, or that time varying phase, is just proportional to the message signal. And for FM, I think I used tau as my dummy variable there. It's the integral of the message signal. So you see there's a low-pass filter going on in my message signal there. So now you know how to turn one into the other. If I have M of t and I build a phase modulator system, then this form will travel down the channel, additive noise, come through the bandpass filter, and so on, and this piece will survive. If I want to turn that into an FM signal, into an FM system, I integrate before the PM transmitter, and then I have to unintegrate or differentiate at the output. How do I realize an integration? A low-pass filter. And how do I integrate? How do I realize a derivative? A high-pass filter. Okay. And over the course of today, and maybe into Tuesday, I want you to think about what it means to put a derivative onto a noisy signal, or to put a high-pass filter on a signal that's fundamentally noisy. Okay? That's asking for it. We'll see just how badly that turns out for us. So this A business here, it is a serious approximation that we say that it's constant, right? Because we already know from our eye diagram, from just looking physically and intuitively at our eye diagram, if this channel is beating the heck out of that, if it's attenuating the heck out of that signal, why should I think that over all time, short durations and long durations, short time scales and long time scales, I'm going to get exactly smack dab the same attenuation on my A. And yet that's what I'm requiring if that A is a constant. So it just seems to me that, over minutes, or over seconds, or over milliseconds, over microseconds, or over nanoseconds, even, that I'll have an induced fluctuation in A. Thankfully, we won't worry about that. Okay? Thankfully, that's just to keep you up at night. Okay? I won't solve that problem for you. That's just something that to guarantee that you wake up at 2 a.m. and worry about it. Okay? Now for the math part of this. Take a look at that guy here, and this form of N of t has a cosine term and a sine term, right? So this is a Cartesian representation, a real part and an imaginary part, a Cartesian representation of the signal. Okay, and this here is a polar form. I have my amplitude and I have my phase angle. So this guy here is a polar form. And so if I write my M of t here or here I guess, and I write my filtered N of t here, I better make sure they're in the same format. Right? It's hard to add a Cartesian to a polar and have everything make sense. So what I either have to do is I either have to convert this to Cartesian, which shouldn't be terribly difficult because it's a trig identity, right? But what I'll do, because you guys would be bored that way, what I'll do instead is, because it actually gives you a nicer way of doing that, is I'll convert this to a polar form. Okay? I'll convert that to the polar form. And so for my noise signal, my filtered noise signal, is a time-varying amplitude. It's a time-varying amplitude times the cosine of the bandpass filter response, omega ct, plus my polar angle, my phase angle. And because it's noise, I'm going to have this wiggling around, and I'm going to have this wiggling around as well. Okay? This amplitude here is the sum of the squares of the in-phase part and the out-of-phase part. Okay. If you need just one more little detail if you need one more little detail, yes, sir.
Is that an N? That's an N, right?
Oh, geez, that's really bad. Now I'll make the mistake on the other one. N sub c squared of t plus n sub s squared of t. And we'll just purge that from the... Is that better? Is that more legible? Sorry, I get so excited that my penmanship goes to heck. If I have a big crayon or marker on the whiteboard, I do a little bit better. Not too much, but I can always do it. So think about what this is, right? A cosine and a sine are 90 degrees out of phase, right? And so when I write in Cartesian coordinates a cosine term, that's orthogonal from a sine term. And that's why the polar form is the cosine part squared plus the sine part squared, square rooted, to get that. Okay? So that you're used to tagging that with an I or a J, square root of -1. But this will work just the same because of the orthogonality of sine and cosine. I finally answered your vortex question today on your thread. Go take a look. This also has to do with orthogonality. Okay. This theta n of t then is just the inverse tangent of the sine part over the cosine part, like that. Okay? So again, this is the polar form. And now I have n of t and I have s and I have my signal of t both in polar form, and I can add them together. The filtered signal okay, that's my message signal with its optimistically constant amplitude. And this is my message signal floating around in here. Think phase modulator. That's proportional to my message signal. And then I add on top of that my noise signal, En of t, cosine of omega ct plus theta n of t. And this is what's going into my demodulator. Okay, this is after the filtering of the noise. So polar form added to polar form. And this is for me, one of the hardest figures to draw. And I'm short one color. That makes it even worse. But I have some axis. And if this is a phasor axis, a complex plane, right? Real, imaginary. What my signals are doing, well, what my FM signal is doing is it's wandering back and forth at a constant amplitude. Usually many cycles, right? But the long trajectories of this is sweeping out the message signal. Okay? And that's the interpretation of what this guy is doing. So at any instant of time, I have a vector, and it's separated from the axis by a time-varying phase angle, by a time-varying angle. And the length of this vector is, put you guys on the spot? A. Excellent. So that's my message signal. And so what's happening is this is wiggling around many cycles in a very, very complicated trajectory that's defined by this. And that's spelling that trajectory is spelling out the content of the message. And I'm adding to this, if this is a vector, I'm going to have vector addition. So I'm adding to this another vector that's moving around the axis with an omega ct plus a theta n of t. So if I were going to draw this, I would have another vector sort of sitting right in here, and it would be wiggling around in a very, very complicated way, governed by this angle here. Oh, and it also has it also is breathing in and out in length. It's also breathing in and out in length. Okay? And the way I'm going to draw that is I'm going to assume that this term is smaller than this term so that I can make some hand-waving approximations. Okay? So I'm going to add this vector. I'm going to add this vector to this vector. So I'm going to put this vector tail to head on that. So this is going to drive you crazy, and it should, but in a good way. The message signal, the black line, is going to be wiggling around in its own weird trajectory. Okay? Maybe you can think about that as a fishing rod moving up and down or something like that. And then at the end of this, is you've got another vector, and it's going to be wiggling around in its own way, and it's going to be breathing in and out in amplitude. And so the sum, y input, is going to be this point right here that's going to have some crazy dynamics to it. Okay? Just to be a little bit clearer, let me label some stuff. I'll draw this guy here, and I'll point out that this angle here is my omega ct plus theta n of t. Right? The angle that this makes to the horizontal axis is this guy here. If this were a vector class, you wouldn't have any problem with what I'm doing. But now that you're juniors and seniors, those angles are now time varying, and that's kind of giving you a nice warm feeling in your belly, I think. Right? A little bit of excitement going on. Hopefully. Okay. Okay. So that's this angle here, and you can see that as this changes, that angle is going to wiggle, and then this amplitude here, and this is, I have to draw this carefully, is En of t. Okay. So the angle, the distance from here to here is time varying, and it's this amplitude right here. Okay. And the resultant vector is the line that goes from here to here. And so let me try to draw that. Let me try to write that down. The resultant vector R of t I'm sorry. The resultant vector yi of t is equal to the amplitude r of t. That's this magnitude here to here, the blue line. Can you see colors reasonably well? Almost. And then it's going to have a cosine term, and not too difficult to imagine the omega c term there. It's here and it's here, so you start thinking about trig identities. The message signal I want to make sure I leave available for identification in my analysis. So that's this term here. And then I'm going to treat the variation on the angle due to this movement of the red vector as a perturbation on that angle. So the form of the resultant vector, the addition of the message to the plus the noise, is going to be an amplitude that's varying, and it's going to be moving with the omega ct oscillation, sweeping around and around and around, and then changing rates due to the message signal, and changing rates again due to the addition of noise. And so to get the angle, I'm going to continue that out there. I'm going to drop a 90-degree angle here. And let's see. The angle will be the theta noise of t minus psi of t, so that this line here is En of t sine of this difference of this triangle here, theta n of t minus psi of t. And that will allow me to estimate the delta psi of t of this now right triangle that I'm approximating that. In other words, and this draws a criticism of this analysis. It's very valid criticism. If A is very, very big relative to the magnitude of the noise, then there's no difference between this red line and the blue resultant vector that's dropped along that right angle. Okay, and so I can argue then that the angle of the opposite over the hypotenuse. The opposite over the hypotenuse is of this vector here is given by that term there, and that allows me to estimate what this variation angle delta phi is. Okay? And so what I'm saying is, if noise is very small, then I can linearize the sign and estimate what delta psi is. But hey, let's face it, if the noise is very small, why am I really worrying about it? We saw in our digital work that a signal to noise of only 2 or 3 or 4 gave us, really good bit error rates. So clearly we're interested in a little bit better analysis. But this is for pencil and paper and for a first cut through. you could imagine getting this term of the expansion and then adding a perturbation on top of that and converging to a more serious one. I mean, look at it this way. You're hired to do this analysis. This is only going to take you the first hour of your workday. You've got 7 more to do. You might as well do the higher order terms. I kid. I'm thinking like a 1930s designer that worked for Armstrong. Anyway, the tangent of that perturbation angle, opposite over adjacent, opposite over adjacent, to get that guy there. Linearized is approximately equal to delta phi of t, so tangent of theta is approximately equal to theta. Sine of theta is approximately equal to theta, and cosine of theta is approximately equal to 1. So sine over cosine is approximately equal to theta. It's just the first term of the ratio of the series. And so this is going to equal En of t times the sine of theta n of t minus the message signal all over A. Okay, so that gives us a formula, an approximate formula for what that angle's doing. And now it becomes dirt simple. Now this becomes dirt simple, because in this analysis, the next step we just solved for that. The next step is a perfect demodulator. Okay, it's a perfect demodulator, which means it just reaches in and nabs whatever my message signal is. So in my very idealized theory, I'm going to assume that I have a perfect demodulator, and if I say demodulate this, well, it's just going to say give me my message signal, and just give me that angle, whatever angle is sitting right there. Well, for a perfect demodulator, if I look at this guy here, instead of just taking the psi of t, it also takes what the contribution due to the noise. So a perfect demodulator, and I'm using a very technical term, it reaches in and it grabs this. Okay? That's what you ask for a demodulator to do. And now it can't say what the variation is due to amplitude or due to the message versus due to noise, because we know statistically, stochastically, they're the same. So that's what it's going to be. So if I draw y input of t, perfect demodulator, y output of t, so y output of t is equal to psi of t plus delta psi of t. Signal, noise. Well, I guess I was using red for noise. Okay. Okay. Like I said, there's a lot. There's a lot there, right? There's the polar form of the mathematics. One thing I just want to circle back, just to remind you again, is this omega CT comes from the nature of your transmitter. There's going to be a local oscillator there. Okay. This omega CT comes from the fact that because I've chosen omega sub c, I'm going to put a bandpass filter in to filter, to pre-filter. Okay? So even though this is the same as this, they come from different sources. Okay? Just to get you caught up a little bit. Questions? Yes, Ryan. Ryan?
Since that means we would want a relatively high, forgive me for restating, but a relatively high amplitude of the term, that A term that was on there.
Oh, yeah. So that's right. Now that's the length of this vector relative to the length of that vector is what you want to have high in order for my linearization to work. In order for my I call it a paraxial approximation. That's a bad, that's an optics word. It doesn't belong here. But it's it's this projection, fudging over that projection is what you're doing, and that requires that A be very, very long. But let's face it, you're going through a channel, and that channel, the whole job of that channel is to grind down A. And what you're interested in is you're interested in the shortest A, the smallest amplitude at which you can resolve your signal, which generally means it's going to look a lot more like the drawing I drew, or worse. I mean, really, you really should be thinking that, if this is a measure of your signal, and then really this vector should be 80%, 70%, 50% of this guy here, right? Which means that this approximation is really, coarse. It's only the first term of the whole problem. Okay, and that's what I mean by saying you do this analysis and then you go back and you keep the next order term of your Taylor series and so on. Okay.
Is there any way that's experimental of seeing when people are implementing systems?
Okay, so that's a really interesting question, right? Can you see this experimentally? You said, are you forced just to do it experimentally? And the question I have for you is, can you see it experimentally in these angle modulated systems? Because you've so intertwined because of the way you've coded, you've so intertwined the noise with the signal that only mathematically can you say you can point to that term and say, here's my signal and here's my noise, because by the time you're detecting it, you're only seeing the sum of the two. And if I tell you that here's $5, you don't know if 4 of it is signal and 1 of it's noise, or 2 of it's signal and 3 of it's noise. Okay, so that's a really interesting observation. Is you can't go to your experiment. You're like me. You always want to see it on the oscilloscope, and before you're comfortable with it. But it's not going to happen. Noise is that insidious. It just really bleeds all the way in there and mixes it up. It's like taking this is not an outrageous analogy. It's like taking a nice glass of water and putting a drop of ink in it. For a while, you can see the clear parts of the water and the ink, but you shake it a little bit, and all of a sudden the ink is dispersed throughout the entire water. It's a nice pale blue, and there's no way that you're going to be able to drink only from the clear part and ignore the blue part. It's all mixed in together. But clearly, you know that there's some part amount of it that's signal or water, and some part amount of it that's ink, and that's what's going on here. And by the way, the entropy of that system, starting to use words like entropy and mixing of that system, is not too distantly related from the thought processes here. Okay. All right. I do want to move along. We'll be explicit now, and we'll say that I have phase modulation, so that psi of t is proportional to my message signal. So y output of t is now my message signal, kp times my message signal, plus the noise over the amplitude of the received signal, the received message signal. And this guy here is what I mean by delta psi of t. So if psi of t is slow, well, I don't even have to say that, but I will. If psi of t is slow, then I can view that as sort of a stable angle around which this is oscillating. Sort of the way I drew my figure. So at any instant of time, I've got this guy sitting there, and this red line is wiggling all over the map. And so that allows me, when I do my trig substitution here, and I guess I should stick a little noise in there, a little n for noise in there. And I want to close my parentheses. So sine of A minus B, sine of A, cosine B, cosine A, sine of B. Odd times an even times an odd, gives me back an odd function. And then I have to hope I remembered the minus sign right. And so now turning this back to Cartesian coordinates, except at baseband, allows me to interpret this term here as the amount of noise. And this term here is the amount of the in-phase noise. So now this is all at the voltage level. And to get my signal to noise, I need to square it and integrate it to get my power. It's the same in the time domain or the frequency domain. Okay. This square means I'll have this term squared, and the cross term. Okay. I don't want to rush you on that. It's a lot of writing. But it's simple. Conceptually, I've got this term plus this term squared, x plus y squared. So I have an x squared, I've got a y squared, and I've got twice xy. Yes, sir?
Would it be like psi of t or just psi?
Yes. Yes, yes. The answer, the question is, should it be a psi of t or a psi? And my answer is yes. It should really be a psi of t. It should really be a psi of t. But generally, when Lati does this, he'll say, assume that the noise, assume that this guy is much faster relative to this guy here. So we're going to look for an adiabatic. This is adiabatic, and this is a faster one. I don't think you have to say that, and I also wonder how general it is. Put it another way, I don't believe it. I don't agree with it completely. But it's again, I'm assuming you're reading the book as well as listening to my lectures, and so but trust me, Lati is really good. So I'm just trying to reconcile the two. Okay, but yes, so if you absolutely should be thinking about this as psi of t, or except all right. So now, what do you think happens to the middle term here? What do you think happens to the middle term here? Why? Orthogonality. Especially true if this is psi of t and sine of psi of t. Very easy argument to make that this guy is the other interpretation of this. The other interpretation of this is a noise term, and this is a noise term, and they're going to be completely uncorrelated. So the consequence that these guys go to zero is that they are uncorrelated noise terms. In other words, the in-phase part of the noise has no knowledge of the out-of-phase parts of the noise. Why? Because it's noise. Okay? If I think about this from a Fourier perspective, the power that I see for the in-phase noise and the power that I see for the out-of-phase or the quadrature noise is going to be the same whether I measure it in the time domain or the frequency domain. And so this power term is going to be the noise magnitude that's out of phase, weighted by this cosine squared term, and the noise power that's in phase, weighted by this sine squared term. What did we decide last time about the relative amount of this guy versus this guy, the amount of in-phase noise versus out-of-phase noise? On average? The same. The same. Phase is going to vary all over the map, so half the time we're going to register it as closer to the cosine, and the other half the time we're going to register it as closer to the sine. So this is going to equal Sn, I'll just pick one, over a squared. Now I'm left with a cosine squared of phi plus a sine squared of phi, and that's going to equal a big old 1. So the noise out is going to be integrated across B. Why is that the limits of my integration? I'm at baseband. Somebody said it, I think, right? Yeah, you muttered it. You shouldn't yell, but I just caught it. You're right. We're at the other side of the perfect demodulator, so we're back down to baseband. So I don't have to worry about the extended frequency spread. Okay, beta has been swept out of the equation, and this is my noise spectral density. So this is equal to twice B times the flat noise level over A squared And that's for flat-topped / white noise with a power spectral density magnitude of n, script n. The signal level is just going to be the kp squared over m. Let me see if I can find that for you easily. Yeah. This is at baseband. Here's the noise term that I've identified and able to pull out what the power is there. The signal is just going to be the power that's floating around in there. And now you can see the role that kp plays in my signal-to-noise ratio. It's huge. So you want, the bigger the k is, the bigger my signal is, the bigger my signal-to-noise ratio is. Very counterintuitive. So the further I spread it out, the more I spread it out across the frequency space, that's what kp is doing, the stronger my signal is, and extensive, and therefore, S out over N out is equal to A kp squared, power in my message signal, over twice N times B. And if you look back, that's not too dissimilar. The 1 over capital B, the 1 over the bandwidth of my system, the 1 over the natural bandwidth of my system, that's very similar in form to the amplitude modulation. So the bigger the B, the bigger my message signal bandwidth is, 1 over B is how my signal-to-noise ratio drops. Okay? So, proportional to 1 over B, it's also proportional to kp squared. That's very interesting. Yes, sir?
A squared?
Oh, sure. Yes. Yes. I should have had parentheses around both of those. Oh, well.
What is M hat?
Okay, so it's a fudge. I have kp times mft. This is my signal part, right? Okay? So kp, when I take the magnitude of this, when I take the power of this, I've got to square this whole thing and integrate it over time. So the kp squared I know what to do with, but this mft is all over the map, so I'm just going to have to label it. And so I label it the average value of m quantity squared. Okay? The average value of m quantity squared. Okay? The DC voltage of the DC level of my volts. That's a little bit sloppy, but you know what I mean. The peak of the sine wave squared. Okay? All right, good. I can. This, and let me just point out. This is for phase modulated. Okay. Now, for FM, I take my PM and I sandwich it between two filters. Sorry. Integration. Because that's what this formula tells me to do. The exponentially modulated, or my angle modulated system, This term here carries my message signal. If it's phase modulated, it's linear. To make a FM signal, we have to integrate it first. If I integrate it first, then I have to differentiate it at the end. So I take my PM case, and on the input end I slap an integration operation, and then on the output end I undo that integration by taking the derivative. Another way to put that is, with this system here, the system there, or there, will be A cosine of omega ct plus kf times the integral of m of tau d tau. Okay? It was kp times m of t, but I've filtered it in up front. So my signal out for the FM case is going to be kf squared times m bar squared. But and that will recover back exactly my message signal part. So that doesn't hurt me any. The same form as I had for the phase modulation. But now take a look at my N out, the power spectral density. That's going to be d by dt of the N out as a function of time for my phase modulated signal. I should have a little bit of more time. Yeah. Don't I? Yeah. Okay, sorry.
Do we add an NFT to the adder in the plot diagram?
Do I add an NFT? Oh, yes, absolutely. Absolutely. Very, very good. Yeah. Sorry, it was in my head, not on the paper. Silly me. That's why I need you guys. Now, if I Fourier transform this, d by dt Fourier transforms to a j omega, right? And just to remind you, this is a voltage level, not the power level. It's the voltage level, right? So bad things happen, and they happen twice. So if I write this n out for FM as a function of omega, that's now equal to j omega times the n out phase modulated of omega. And this is my power spectral density, which means I have to integrate it. So this is a voltage, and that implies j omega squared for the power. One for each voltage, right? B squared over R. So if I have a j omega for one voltage and I have a j omega for the other voltage, I square that frequency dependence. So now, to get my noise out, I have to take my flat power spectral density. I have to integrate omega squared d omega all over that a squared. And I have to integrate over the bandwidth, 2 pi b. This is to get my noise. That's the denominator. This is not good. This is equal to 8 pi squared times the same noise spectral density that I had for my PM case. I now have b cubed because omega squared d omega gives me an omega cubed. And the only thing I have to counter that with is a lousy 3. And just put all in perspective, my signal-to-noise ratio for my FM case is equal to 3 kF squared, the average value of my message signal, over 2 pi b squared, a squared over 2, n times b. So this guy here and this guy here is what I had before. And now as I increase my bandwidth of my signal, I drop my signal-to-noise ratio substantially. So this whole thing is now proportional to 1 over b cubed. So for my AM case, for my baseband case, and for my PM case, I went as 1 over b. And now I'm going as 1 over b cubed. So the wider I open my window, my bandpass filter, right? Just my B, my fundamental B for my message signal. The more frequency content I carry, for the phase modulated case, my signal to noise just drops linearly, 1 over b. On the other hand, now I'm going by 1 over b cubed. So twice the bandwidth now becomes 1 over 8th the signal-to-noise ratio. So much more, slightly more aggressive function. A more aggressive function. Okay? All right. That's actually a pretty good place to quit. Any questions? Yes, sir.
You talked about the class one time about the growth in signal electronics and the third-party activity about need to ask you to talk to the class about it.
Oh, say that again then.
The 3 topics we're going demodulation like microelectronics and telecom and a third section of it. And you said we're all going really quickly.
Yeah. I think I know, but I'll talk to you about it. I'll talk about it some other time. But I understand what you're saying. Ryan, did you have a question?
Just since the obviously want to put out a higher power, the A squared term.
Yep.
We see the bandwidth relationship. But how do we change the K?
Okay, so K is going to be I think if you look at the Armstrong method, K was an amplification, how much gain you got in an amplifier. And so the higher the gain, the more it's spread out across the phase space. So that's a design parameter that you can program in, straightforwardly. Okay. Okay. I'll see you Wednesday for our last class.